Good afternoon. Welcome to our talk. Today we are going to speak about application of generative query networks for industrial time series. Before going into the details, technicalities related to the talk, who we are. My name is Rafał Bachorz, and I'm a head of advanced analytics team in PSI Polska. And there's also Grzegorz, who is data scientist in my team, in advanced analytics team, also at PSI Polska. So let's go through the agenda. What is the content of this presentation? We are going to talk about the application of generative query networks. Therefore, in the first part, we would like to introduce the generative query networks. Then a few words about time series forecasting time series predictions with static metadata. Then a few words about the business context, so why we are interested in this sort of use case or this sort of technique. This will be illustrated in this, let's say, background associated with pipelines and leak detection systems. And then just before the end, the results, and as usual, at the very end, the summary of the talk. So let's go to the very first part, which is a generative query network. What is that actually? This is a very neat idea, which has been published 2 years ago, roughly, in Science. This is a very good paper, by the way, so if you want to read something nice, I really recommend this paper. This is a paper, the use case inspired by machine vision, and in principle, it is focused on the situation or the use case where you have, let's say, the pictures, the visual representation of some objects in some room, for example. But you take into account not only the pictures themselves, but also the meta information associated with the picture, which are this let's say, objects. And so you have a lot of this, images which are accompanied by this meta information, and you somehow introduce this into the neural network, broadly speaking. And principle on the right hand side, you have this graphical representation of this network, and as you can see, it is composed by two components, so to say. You have the representation network and the generation network, and what is going on is that you simply take the pictures together with this meta information, like here, these two pictures with VI1, VI2, and this meta information, this is, for example, the orientation of the camera. So you take the picture and you somehow quantify the aspect of the orientation of the camera. So you can somehow define the orientation of the camera, and this is this associated information. And the same with the second example. You take another picture from different, let's say, side or so, or from different perspective. You also attach this V component, and you pass it through, supposedly convolutional neural network in order to get something like an latent representation, which is afterwards simply summed up in order to create this neural scene representation, which is this latent representation of all these pieces which are provided here, and there might be, let's say, an arbitrary number of them. And then you introduce this into the second neural network. So you take some number of these examples, you take the generation network G, and what is important here, you introduce, let's say, another meta information associated with a different perspective or different orientation, the one which is expected by you. And the neural network is trained in such a way that everything is put together and trained jointly in such a way that afterwards, in the inference phase, you can just introduce data together with this expected meta information, and you get the scene which is expected by you. And this is a little bit more detailed picture of that. So we have a training examples, as it was discussed on the previous slide. We have the pictures, the images X, and the viewpoints V, and they are composed together, combined, in order to create the observation, the observation with an index I. And exactly as it was shown on the previous slide, you have some number of these observations, defined like here. You put them into this the first part of the architecture, which is the representation network. You create this neural scene representation, which is here introduced as a vector R, which later on is provided to the generation network, and together with this additional hint, additional supportive information about the expected orientation you want to get from the network, or in the training phase about, let's say, the orientation of the training example, which is currently the subject of the training, and everything is trained in such a way that afterwards, in the inference phase, you will provide some latent representation of some pictures, plus this meta information about the expected orientation, and you will get this expected orientation. The picture, let's say, reflecting the expected orientation. Okay, and that's it more or less. So this is the main idea of generative query network. In this case, it was a machine vision use case, but we find that it can be useful in many other areas, and one of them is going to be presented in the following slides. So now I'm passing the voice to Grzegorz, who is going to introduce to you, let's say, the time series with static metadata.
So our main aim was to use this approach, but replace images with time series. So can we go to the next slide? So the whole architecture remained as it was, but instead of images, the time series with corresponding metadata are passed to the model. Then, as it was before, encoder produced the latent state, and this latent state is later enriched with metadata, which is kind of query, and then decoder produced this time series instead of an image. And this approach can be used in many different ways. One of them is traffic prediction. When given traffic from different roads, one can predict how many cars, for example, are present on the another when there are no sensors. Other approach is energy consumption, when you can somehow predict what is the energy consumption based on sensors from other buildings, other companies. I think the most obvious application is weather forecast, when you predict weather based on the weather in other places or other sensors. And the use case that we will describe later on in this presentation is pressure in pipelines, where we predict the value of pressure based on sensors located in some predefined points in the pipeline. The original approach used convolutional layers, since the images are object of training and prediction. And because we use time series, then we use appropriate recurrent layers. The two mostly widely used ones are LSTM cell and GRU cell. Here we use the first one, but the other can be used as well. As you can see in this image presenting the LSTM cell, there is a quite complex one. There is some maths inside, but we will not focus deeply into it. The most important thing is that there are two states inside an LSTM cell and hidden states, called this way. and they are processing every time a new timestamp is introduced as to the input of the cell. So when we work with an input at a given timestamp, then the states from the previous timestamp are used, then they are updated and will be used in the next timestamp, and this goes when we iterate through the whole time series. And one can ask a question: what is this value of this state at the beginning, since there were no previous timestamps, so we don't have any value. And this is so-called initial states, which is by default equal to 0. And our idea was to use it to inject this static metadata into the LSTM cell, since it can only work with the recurrent data with the time dimension, and there is no obvious way how to use the static metadata here. This is how we want to do this. There are two basic problems. First one is the dimension, since we will need as many values, these initial values, as we have LSTM cells in a layer. So it will usually not match the size of our static input. And the other problem is that we don't want to hard code this value anyway. We want them to be trainable parameters. We want them to take part in the backpropagation algorithm. And we solve both of these problems by introducing between the static data and the initial state a dense layer, so the typical ones actually, which firstly transform data into a given shape, and what is more, they transform them into different values using weights in these dense layers, which are part subject of the training. So during the training phase, model learns how to transform the static data into initial states of an LSTM layer in such a way that the results are the best. And this approach was recently published by us in the paper in the Neural Processing Letters. So if someone is more interested, want to dig deeper into this problem, then here is the reference. And we exactly use this approach. Of course, we stack multiple LSTM layers, not only one. And this architecture was used in both encoder and the decoder state. And we have to change one more thing. It's a small change. Instead of inputting the time series and metadata one by one, we merge them into pairs, but it's a not huge change. The architecture remains the same, only the size of an input is larger, twice as big. And later on, we will describe why we need to change this. So to compare our approach with the previous one, the first approach, the original one, we have a scene represented by images. And now in our use case, we will have a pipeline with some hydraulic states, some hydraulic events, which are represented by pressures measured at a given point. And our metadata describing the observations are now not the position of a camera and the orientation, but the position where we want to measure the pressure and the time. So we introduced another dimension, which is time, which is very useful since we can predict future values as well using the same model. Now we will describe deeper the business context of this use case.
Okay. Yeah, as you can see, there is a clear analogy between this initial effort, this machine learning use case, and our use case. And now we would like to say a few words about the reasons why actually it's interesting for us. So this is a pipeline. Actually, we at PSI we work a lot with pipelines. Pipelines carrying various media, single and multi-phase liquids. for example, the crude oil, final petroleum products like fuel, diesel, and so on. The multi-phase reservoir fluid, which is a mixture, pretty complex fluid, by the way, for the modeling, which is a mixture of crude oil and the natural gas. So we have at least 2 phases here, sometimes even 3. And the software, one of the responsibilities of the software we deploy at the customer sites is, let's say, verification of the pipeline state based on a set of process measurements. In order to gather the measurements, we usually use the SCADA system, supervisory control and data acquisition, which are responsible for exactly the data acquisition. And we might have the various, let's say, signals like pressures, flows, temperatures, and so on. And we take them in order, for example, in order to check whether there is a leak or not. So we also, let's say, nearby of SCADA system, we deploy the leak detection and location systems, which exactly are responsible for, let's say, inferring whether there is a leak or not. And if there is a leak, then the system is obliged to provide the information about the leak location. In principle, the pressure, one of the leak detection methods is the pressure search method, which is pretty simple actually, because it relies only on the pressure signals, and it relies on the let's say phenomenon which is occurring when the leak is happening. So assuming that between P4 and P5 we have a leak, then an orifice, a hole, for example, is formed somewhere here. And this, exactly in this particular moment, there is a mechanical wave is formed, the pressure wave, the negative pressure wave, which travels in both the directions, I mean, towards P4 and P5 with some speed, which is, so the pressure wave speed, actually quite similar to the sonic velocity, but not exactly the same, but this doesn't matter. But it might happen at some point that this pressure measurement is gets unavailable because it is broken, or there is some problem with the transmission of the data from the fields to SCADA system or something like this. And especially in the context of the pressure search method, this is pretty unfortunate because it happens pretty quickly. I mean, the wave travels with a speed of 1,000 meters per second, more or less. And if this measurement is unavailable for a couple of seconds, then unfortunately, you miss your only chance to get the leak. But we have the other measurements. Assuming that, let's say, majority of these measurements is available, and having in somehow on site prepared the predictive model based on generative query network, we can simply try to recover the signal exactly from the model. And this is the main idea and the main reason we think about this methodology in the context of pipelines. As Grzegorz mentioned before, there are also the other areas, like, broadly speaking, forecasting of, for example, energy consumption, and so on and so on. So this is not the only use case which came to our mind, but this is, to be honest, the first one, and yeah, this is exactly the reason why we are looking at this technique and find the results very promising. And now we'd like to go through the results. And again, I would pass a voice to Grzegorz. Grzegorz, we cannot hear you.
Sorry, I was muted. As promised before, we will quickly describe why we have to change the input of the model. So our first result, as you can see here, there was a slightly important mismatch in the time domain. And after we discuss it, the problem is that there is a different time of the event wave propagation in different media, and since the model receive the data one by one, then they can't infer the speed based on singular input. That's why we have to input pair of time series, and then the speed can be deduced and the model works perfectly fine. And here we also mention some not very important parameters about the model as size and time of training. Actually, even after 3 hours of training, the model give very good results, but we waited till it converged to the local optimum, which takes additional 12 hours. And now we will present some final results. The convention will be always like this. So firstly, we present 3 plots of the observation that were given to a model, and then the result of the prediction, as well as the real value that models need to duplicate in this case. So as mentioned before, when given pairs of observation, model works very good. There is just very little difference between the simulation and the real value, which probably comes from the noise. And the model is capable of doing what we wanted them to do, so predicting the pressure at given position and time when exposed on the data from other sensors. And model can deal with many situations that occurs in the pipeline. One of them is different topology. So in some points, the base value of the pressure is higher, while on other it's lower. Other problem is that some sensors can record only part of the event, as we can see this in the, for example, observation 3, where only the second part of this event is recorded, but model still works perfectly fine. Another example, here we can see a huge change in the amplitude between the prediction and the observation. It's because the place for which we want the prediction was far away from the place where the event occurs, but still model can work with it, which can lead to another promising feature, that we can use this approach to determine the exact position of the event. So using this, we can find where is the leak, for example, since the model learned this physics about the wave changing, the amplitude changing while being far away from the place of occurrence. Here we can change a difference in this base pressure. So some places in the pipeline when we have sensors are higher when we talk about the position above the sea level, while the other places are lower, which influence the base pressure. But the model simply learn the topology of the pipeline and can deal with this situation very well. And this is the last result, I think, where we actually see all of these previous factors I mentioned. So we have only part of pattern in some observation. We have difference in the base pressure as well as different in amplitude. And the answer given by a model is very good still.
Yeah, it was the last, but one. This is the very last, and yeah, it's more or less the same. Let's say picture. The one sentence of a summary from my side. I mean, it is quite neat that it is the predictive model, or we were able to embed somehow the physics of the pipeline, or some, let's say, some subset of the physics of the pipeline in the predictive model, and it is behaving satisfactory. I mean, it provides satisfactory results in both domains. In the time domain, which is on this horizontal axis, so we see an appropriate shifts between this plots, but also in this quantity domain, which is a pressure domain. So we also see that it is capable of learning what is the attenuation factor, how, to which extent the amplitudes of the pressure wave get smaller and smaller when traveling along the pipeline. So yeah, this was simply possible to embed, as I mentioned, the physics of the pipeline in the predictive model. And this is the very end. So we have arrived to the summary. So yeah, as you can see on the right hand side, we've gone through the talk. We introduced the generative query networks. Then we discussed the time series with static metadata. We also sketched the business context, the pipelines and the LDS system, the SCADA system, and so on, the things which are interesting from our point of view. Then we've shown you the results, and we are here at the summary. So thanks a lot for your attention, and if there are some questions, we are eager to answer them. Thank you very much.
So, thank you, Rafał and Grzegorz, for your talk. It was very interesting. We have one question from the audience, so I will read it out loud. And the question is, what was the pressure prediction horizon expressed in minutes?
So in this particular case, it was a couple of seconds. So there's on the x-axis we had the samples simply, and the basis, the data was the pressure given in 10 hertz resolution. So yeah, in this use case, it was interesting to see the phenomena which are spanned somehow on let's say a couple of seconds horizon, and this is purely associated with the use case. So the LDS, the leak detection system, which was shortly discussed, it was based on the pressure surge method, which means that we are simply looking or trying to look at the pressure wave which is traveling along the pipeline with speed roughly 1000 meters per hour. Therefore, from the perspective of the use case, it's interesting to, let's say, capture a couple of seconds, something like 5 seconds. But of course, this is not the limitation. So I think that this pretty much depends on the, let's say, subset of the physics you encapsulate into the model. In the case of other use cases where we would be interested in let's say slowly changing quantities, I think it would be possible to train the model, to deliver the data and train the model in such a way that we would capture the phenomena on longer time horizon.
Okay, thanks. And I have two questions from my side. So the first question would be, well, if you incorporate the state information within LSTM in a way that you showed us on slide number 9, I guess, does it learn faster or with less amount of data, or is it like just a method to include the static information in the model? Have you observed any kind of relationship between time of training and, yeah?
Go ahead.
We didn't test it in this approach. Because this was a subject of our previous research, the paper we cite somehow in this presentation. And this approach was the most sufficient in case of the metrics of the model. So we tried different approach of incorporating the static data, and this particular one provides the best results. So I don't remember if the time of training was different, but after the model converged, after it find the, let's say, optimal, so suboptimal parameters, the prediction were the most accurate.
Okay, that's quite interesting. I would like to further ask about any other ways that you tested of incorporating this static information within the LSTM layer, because I guess there must be more than one way.
Yeah, of course. Yeah, this is the final one, and what we tried was just to transfer this, produce this 2 dimensions separately. So transfer time series with LSTM or GRU layers and the static data separately with dense layers, and then just at the end concatenate those 2 values. But in this approach, when we process the time series, we cannot use the static data, which sometimes may be useful.
as in this case it was, for example. And the very basic approach how to avoid it was to just add this static metadata as a first timestamp. But of course, it was not very sufficient since it's just comparing apples with something else. It doesn't matter.
Okay, cool. Yeah, thank you for the answer. I guess we've run up out of time for the Q&A session. So thanks again for this great talk and the answer to the questions.
Thank you.
And yeah, our next speaker.